Welcome to lesson 33, Capacitance and Energy Stored, components that store charge and release it in a burst. Here's the plan for today. Start with the word capacitance. The root is capacity. How much can it hold? Here's the picture. Take an ordinary circuit loop with a cell and cut the wire, leaving two plates facing each other across a gap. Now the electrons can't complete the loop, so they pile up on one plate. That plate becomes negatively charged, while the other, having lost electrons to the cell, is left positive. The two plates carry equal and opposite charges, and we call the magnitude of that stored charge Q. Note that the capacitor as a whole is still neutral, it's just separated the charges. Now, if you push harder, apply more volts, you can force more charge onto the plates, and that turns out to be directly proportional. Double the voltage, double the charge stored. So the useful thing to measure is the charge stored per volt. That's the capacitance, big C. Q equals CV. And note the direction of that ratio. It's charge per volt, not volts per coulomb. Get that the wrong way up and everything after it collapses. But what are the units? From the equation, coulombs per volt, and we give that a name, the farad. Now, a farad is a huge amount of capacitance, so in practice you'll almost always be dealing with microfarads. Make sure you watch those powers of 10 in your calculations, and if you're unfamiliar, check out lesson 1. Now, how much energy does a charged capacitor hold? Here's the subtlety. As you add charge, the plates already have charge on them, so they push back. Every extra bit of charge you add has to be pushed against the potential difference that's already built up. So the energy for a small bit of charge is V times that small delta Q. And to get that total, you sum all of those up, which is to say you integrate V with respect to Q. Graphically, that's the area under the charge voltage graph. And because Q equals CV, that graph is a straight line, so the area is just a triangle. Half base times height, giving a half QV. Then, by substituting Q equals CV, you can also write it as a half CV squared, or as Q squared over 2C. 3 equivalent forms of the same equation. Learn all 3 and pick whichever matches the quantities the question hands you. Here's the single most useful exam tip in this topic, and it turns hard questions into easy ones. Capacitance C is normally fixed by the physical capacitor, so when a question changes something, ask yourself, what else is being held constant? If the battery is disconnected, the charge is trapped on the plates. It has nowhere to go, so Q stays constant and it's the voltage that changes. But if the battery stays connected, the supply holds the voltage fixed, so V stays constant and it's the charge that changes as the battery pushes more on or pulls some off. Decide which case you're in first, then pick the energy equation that has your constant quantity in it. Occasionally they'll change C instead, but the same logic applies. One more example, and it's a lovely one. 2 plates carry opposite charges, so they attract each other, which means if you want to pull them apart, you have to do work against that attraction, and that work has to go somewhere. Think of a thundercloud, where the charge is fixed. With the charge held constant, the electric field between the plates stays the same, but the voltage is the field times the distance, V equals ED, from last lesson. So as the separation D increases, the voltage must rise. And since the energy is a half QV and V is E times D, the energy is a half QED. Be careful with the E's here. So pulling the plates apart by distance delta D increases the stored energy by half QE delta D. The work you did pulling them apart is now stored in the capacitor. Energy conservation, exactly as you'd expect. That's the end of the video. Thanks so much for watching, and check out my tutoring page below.